Section 3.3, Rules for Differentiation. We are going to learn 6 new rules, shortcuts for taking the derivative. Today, we will prove 2 of them. We don't have time to prove them all, but all 6 of these fall out from the same type of proof, coming from the definition of the derivative. So we're going to start with our x to the n function, and we want to prove the derivative for x to the n. And we start with the definition of a derivative, which is the limit as x goes to 0 of x plus h to the n minus x to the n all over h. And the next thing we would usually do is expand out x plus h to the n. Well, let's think about if we had x plus h cubed. That would be x cubed plus 3 excuse me, x squared h plus 3xh squared plus h cubed. Well, if we expand x plus h to the n out, it follows the same pattern. We would have x to the n plus n times x to the n minus 1h plus a whole bunch of terms leading us to h to the n. And what we need to note is that everything after the first term would have an h in it. So now when we come back here and do our limit as h goes to 0 of x to the n plus n x to the n minus 1 h plus a whole bunch of things ending with h to the n minus x to the n all over h, we get some nice canceling to happen. The x to the n's cancel out. The next thing we would do is factor out an h on the top, leaving us with nx to the n minus 1 plus a whole bunch of terms with h's, leading us to h to the n minus 1, like that, all over h, limit as h goes to 0. So once again we get nice canceling happening, the h's go away. And now as we take the limit, we let h go to 0, all of these other terms with h's in it go away, and we are left with the derivative of x to the n is equal to n times x to the n minus 1. So if we have something like the derivative of x to the 5th, that derivative function would be 5 times x to the 4th. So that's our first rule that we're proving, which happens to be rule number 2. And let's put a nice example here. The derivative with respect to x of x to the 10th would be 10x to the 9th. All right. Also on this page we have the derivative of a constant. And if we think about a constant function, it's just a horizontal line. And the derivative is the slope of the tangent line, or the slope at one point. And if I take the slope at any point on a horizontal line, the slope is 0. So the derivative of a constant, like 7, would be 0. And then the third rule on this page says that if we have something like a constant multiplied by a function of x, so if we were taking the derivative of of x cubed, then that 10 can come out in front times the derivative of x cubed, which would be 10 times 3x squared, or 30x squared. So there are our first 3 rules. Now we'll move on and take a look at the sum and difference rule. So this deals with when we're dealing with things like polynomials. So basically it says the derivative of a sum or difference is equal to the sum or difference of the derivatives. So if I want to take the derivative of 3x squared plus 2x minus 7, I can take the derivative of each term individually, and that will be the derivative of the entire function. So this would be 6x plus 2 minus 0. We don't need to write the minus 0, but I just want to show that we can take the derivative term by term. All right, the next rule we have is the product rule, and we're going to prove that one as well. This one requires a little bit of math magic. Just one little step that makes it easier to see the patterns. Here we have the derivative of u times v. Well, u and v are functions of x. And we are taking the derivative with respect to x. So x is our variable. All right, so we have the definition of our derivative filled in, u of x plus h times v of x plus h minus u of x times v of x all over h. And the next thing we need to do is our little math magic. And it's a nice little step that makes it easier to see what's going on. So we are going to subtract a term, u of x plus h times v of x. And then we're going to add it back in, u of x plus h times v of x. And by doing this, we haven't changed the expression at all, but we get to see some nice derivatives fall out, definition of the derivative fall out in our work. So now we're going to have the limit as h goes to 0 of u of x plus h, v of x plus h, minus, so now I'll subtract this magic term, u of x plus h, v of x, plus, I'll add it back in, u of x plus h, v of x, minus u of x, v of x. All of this over h. Okay. Now, so really all we added, we subtracted and added this little section right here. And because we subtracted then added it, we haven't changed the expression at all, just its appearance. So now I'm going to rearrange my limits a little bit so that we can see how this falls out. We'll have the limit as h goes to 0 of u of x plus h. And we can factor, the way we pull that out in front is we factor u of x plus h out of the first two terms. And that leaves us with v of x plus h minus v of x all over h. I'm strategically writing it that way. And I'm going to separate this into a second limit plus the limit as h goes to 0. I can factor a v of x out of each of these, leaving me with u of x plus h minus u of x all over h. And if you notice, what we have here is the limit of a product, so that can be written as the product of the limits, limit as h goes to 0 of u of x plus h, times the limit as h goes to 0 of this v of x plus h minus v of x all over h, plus the limit as h goes to 0 of v of x, times the limit as h goes to 0 of this, u of x plus h minus u of x all over h. And what we notice here is that this is the definition of a derivative. That is dv dx. And the limit as h goes to 0 of this is u of x. So we have u of x times dv dx, plus the limit as h goes to 0 of v of x is just v of x, times this is another definition of a derivative. It is the derivative of u of x. So what we have come up with here is called the product rule, where we have two functions, u and v, that we're multiplying, and to find the derivative we would find u times the derivative of v plus v times the derivative of u. You might see it written like this, u v prime plus v u prime. So that is the product rule. And we use that when we are taking the derivative of product of functions. So if we have d dx of 2x plus 3 times 5x plus 8, you could multiply it all out and take the derivative term by term using the sum and difference rule, or we could use the product rule, which is the first, which is 2x plus 3, times the derivative of the second, which is 5, plus the second, 5x plus 8, times the derivative of the first, which is 2. Now on a free response, you could leave your answer like that, and it would be fine. But on a multiple choice, it would be very unlikely that the answer would be written like that. So let's multiply it out. 10x plus 15 plus 10x plus 16, and we get our 20x plus 31. All right, quotient rule. Well, we just found out that when we have a product, we cannot just take the derivative of the first factor times the derivative of the second factor. We have to use the product rule. Well, when we have a quotient, something divided by something, we need to use what is called the quotient rule. And the way I want you to think about this is consider u to be the high function and v to be the low function. And there's a little rhyme that helps us. It is low d high. D high means take the derivative of the high function, minus high d low, the derivative of the low function, over the denominator squared will go. So if I am simply taking the derivative of x plus 2 over 3x plus 4, that is a quotient, and we would do the quotient rule. So we would do low d high, 3x plus 4. D high is the derivative of the top, which is just 1, minus high, which is x plus 2, times the derivative of the bottom, which is 3, all over the denominator squared, which is 3x plus 4 squared. Again, on a free response, this would be an acceptable answer. Excuse me. But on a multiple choice, it would most likely not be written that way. So let's simplify what we can. Here we have 3x plus 4 minus 3x minus 6 all over 3x plus 4 squared. And that is 4 minus 6, negative 2 over 3x plus 4 squared is the derivative of this function. So, those are our 6 rules. And some key examples I'm going to put on the next page. I am not going to put voiceover on that page. I'm just going to give you the examples that you can look at and use as a guide and some helpful hints. And that finishes our video for section 3.3, our first look at differentiation rules. So here's where I'll put our examples. You can stop the video and look at these as you please. So I hope they're helpful. So on this page we have 3 examples here. Stop the video if you'd like to stop and look at them. I'll just scroll through so you can see the whole thing. And then we'll continue on with another set of examples. All right, my final piece of information has to do with horizontal and vertical tangents. And just a reminder, horizontal tangents are where the original function would have a horizontal tangent line. That would mean that the derivative would equal 0. dy dx would equal 0 there. So you need to find dy dx and set that equal to 0. And if dy dx is a rational function, then really all you have to set equal to 0 is the top. Vertical tangents, that would be where dy dx is undefined. Vertical lines have an undefined slope. So to find where vertical tangents occur, you find dy dx, and then you find where dy dx is undefined. So if dy dx is a rational function, you set the bottom equal to 0. For example, x plus 2 over 2x minus 7, if that is our derivative, dy dx, then to find where the vertical tangent lines are, all you need to do is set the denominator, 2x minus 7, equal to 0, and solve for x.